So I've been working a lot on the scripting, and Joel's also been working a lot on LispBM in the past months, and it's starting to get a bit closer to a consistent, stable release now. And I'm going to show some of the things that have happened since the earlier versions that I was demoing before. We can start by, let's start with mentioning a few things about threading. So before, when they had threads, then they were cooperative, meaning that if one thread was blocking, then other threads could not run until that thread would run sleep or yield, so that the other ones could get some CPU time. And that is no longer the case. So now you can have preemptive threading with a round-robin scheduler, meaning that many threads, even without sleeping, can run at the same time. I will demo that quickly here. So we can make 2 threads. Let's call it the first one P1. This is just a function that will spawn it as a thread. This is a function that doesn't take an argument, and we will make it a loop, and here we will have a prog n. By the way, we also have Auto-indentation, the VESC tool editor now, so you can just select everything and do Control I, and then it should get to give you quite good indentation. I will go into that later. So here we will just do define or def, which is the same thing, a plus a1. And since I'm reading a, I have to define it beforehand. And now let's copy this one, call it T2, and do the same thing with B instead. I also have to duplicate this line. And then we can use spawn to start 2 threads, so we do spawn T1 and also spawn T2. And now that I'm here, I can also mention that before you could only do upload, which would erase flash and run it then. Now there's also stream function, which doesn't erase flash. It will upload this and parse it as it receives the data. So it will be a bit faster, it will not wear down flash, and if you have, for example, a control loop running, you can get it running real fast afterwards. So let's do stream, which also has the shortcut Control W. And now you can see them counting up, both at the same time. And we're using a lot of CPU. And both of them are counting, even though there's no sleep in any of them. And before, if you did this, then the first one would start and it would get stuck there because it doesn't yield, and this one will not get a chance to run. I don't really need a prog in here when I do it like this. One problem that you can run into when you do this is that, and usually if you write programs without modifying data, then you never run into this, but suppose you want to have another thing that both are increasing. So let's do this here, and if everything is correct, then C should be the sum of A and B, if this would be working. And it kind of is, but I think it will not really be that. We can try that in Rebel, so we can try plus A, B, and let's print everything, so we do print plus AB and print C. And you can see that the sum of A and B is greater than the sum of C. And the reason that this happened now is because this one will start to evaluate this expression, and it might get interrupted here while this one also does that, and it will it might have read it already, and it will do the addition and write it back, and then this one will write back the same value again. And I think that's called a race condition in multi-threading. And to deal with issues like this, you also have this atomic construct. So you can use for example, atomic around here. And this means when you are in an atomic block, it's not allowed to run anything else until you leave that block. give this a try. And it looks very similar to before. But if we do this now, we can make this atomic as well. Actually, we can print it like this. You can see, yeah, they are more or less the same value. And I think if we make this one atomic, they might be the same value, because then it will not have time to fetch them while it's printing. Yeah, maybe you can get some situations where that happens. So that is preemptive multithreading, and also the atomic construct, so that you can do things, read, modify, write operations. First you might wonder why would this be useful, and the one example that I have seen where this would have been very useful is when you have, for example, some code that draws things to a display which might run quite slow, and you want to sample, say, an encoder at the same time, and you don't want to skip any pulses. Before you would have to split up your slow code so that it sleeps now and then in order for the more critical code to run now and then. But now I don't have to think about that, because things run at the same time with a fair round-robin scheduler. So that is preemption. We can also mention a few small improvements in general. So first, as I said, yeah, we have auto-indentation. When you select things and do Control-I, it will auto-indent them. And it actually works quite well. So even if I'm here and just want to indent this line, you can do Control-I and you will get it like this. We can actually try this on a larger file. So if we take one of the examples and we take the, let's see, the M365-, this one. Now we'll just go ahead and select everything and do Control-I. And it does a fairly decent job of it. There's a few things that I would still tweak here. For example, these if statements, this is on the same line, and that's because this closing bracket is on this line. So if I move this one down here and do Control-I here, it will indent it like this. And I think if you do it like this, it looks slightly better anyway. And that is actually, when you sit and write code here quite a bit, that is a huge help, that you can do the auto-indentation. Another thing that you might see when you have this one open is that we have better and more syntax highlighting. And before we had an issue in the editor that it would split words in minus signs, and well, that's why I didn't have a lot in syntax, because then you could have one word, for example, that starts with UART, and then you do UART dash something else, and this other thing shouldn't be highlighted, but you will highlight the first word in it. And that is now fixed. The other thing I did is that I have added auto-completion for almost everything that is in the libraries, which is probably like 400 different functions and extensions and so on. So you can do like can, get, and you can list all of them, and it will help you complete them. And also, if you go back, it will show it as it goes. So this is really useful. And it also does auto-completion on some things like the pins. So if you start to erase here, then you can see all of the different pin modes, or all of the names that start with this thing. And you see that the pin mode, this thing has a different color than this one, because this is a symbol, or actually both of them are symbols, but this has a different meaning in the default libraries. And yeah, that really helps with you quite a bit when you work with this a lot. There is also obviously more extensions, and there is a speed improvement as well. So most code runs probably 20 or 30% faster than it did before. There are more checks. It actually takes less memory on the VESC now, because some things are optimized. One thing that is really useful that I want to demo here as well is a new statement that is called import. And that is kind of what it sounds like. You can use it in order to import files into LispBM. And that is something that VESC tool handles mostly. And now you can see that this file is saved in this place called demo.lisp. And let's open this OLED driver, and I will do save as, and I will call it just OLED here. And now they are in the same directory, so you can see that we have demo here and we have OLED. And then when you import files, I will show that import Now I will import this file and bind it to the symbol OLED, and it will start looking in the path that you have down here. You can also write an absolute path, but the default it will go down here. And now if I just run this program, now I cannot use stream, by the way, because when I use import I have to upload, because I have to write this file to flash. So this file will live in flash and not in RAM, so you can import rather large files when you do this. Then we do upload. And now if you go to the REPL, you can type env like this, and you can see that we have this OLED symbol here, and we'll just go on and we can print the whole, I think we can print the whole thing. Yeah, I don't think it will print that much because the print buffer has a limitation in size, but essentially this is the entire file that we have here. And we can actually, suppose we want to have this one as a library, then I can remove this this while loop. Actually, let's move it out of here. Save this one, and I will paste this one in here. And now we just have some functions and things in here. And if I upload this one now, this will not work because there's a lot of unbound stuff here. And the reason is that we have imported this file, but it hasn't really tried to read and parse the code. So you can do eval program, and you can use read program, and you can do OLED. And if you do this, this should start doing something. Upload. And it looks like we are doing something. And if we move this one, the screen, the camera in here, you can see that the OLED is drawing things. And if I change the power supply voltage, you can see the circle and so is moving. So now you don't have to have all of the code in here. You can just import the file, and you can have it like a library. And another thing that you could do here is to, I just want to make it clear that now in this file we have some fonts, and they will be, the reader will read them and it will put them in RAM. But you could also put the binary data of this font into a file, and then you could import that file and call it font in the same way, and then this file would be in Flash, and you would have much more space for different fonts and pictures and so on, for example. And import doesn't work. This happened to be a Lisp file, but we can import any file really. And those native libraries that we can load as well. So when you write a C program and compile that, you can import that compiled code and do eval, or you can, not eval, it's called load native library, and load that file. So that is super convenient too. Another thing you can do, I will not talk much about it here I think, but I'm also working on something called VESC packages, where we can have some drivers, for example, that are on a GitHub repository. And from VESC tool you can update this archive, and you can import libraries that are present in this archive. So if you want to share a library and you want to keep it updated for others to use, then you can put it in this repository and you can import. This is also written in the documentation, by the way. There is a syntax where you can import packages or files from these libraries. Yeah, also another thing that might be useful to know about import is that if you have large programs, and for example you have a display and you have lots and lots of menus, and you have a hard time fitting them in the heap, then you can have different menus, for example, as different files, and you can read and evaluate those programs when you need them, because then you don't need to keep them in memory. That's, for example, when you have the things here, we could replace those things that we have, or we can even undefine them. And if we do that, then it will be garbage collected and it will free up the heap memory. I will also not talk about that much in this video, but I think the import thing is a very useful addition to the scripting that wasn't there before. Let's see, we also have some small changes, like you can, for example, when you have lists, you can use negative indices to index them from the back. So if you have suppose we make a list here. Let's call it L, and we use quotation 1, 2, 3, 4, 5, 6. And I will just stream this file so we can access it for the REPL. And if I type L, you can see the list here. And then you can do ix, for example, L2, and we get that element, or we can do ix0, then we get the first one. If we do ix minus 1, we get the last one, which is the same as Python does, and this has turned out to be quite useful for many of the programs that I have written. And there are many small improvements like this. Now I will show a demo of well, how this can be, the scripting can be quite powerful, and how a language like Lisp, where code and data is the same thing, can make some things really nice and convenient for certain tasks. And one of those tasks is the logging. So I have this other video with this logging module, and we have a demo of that here, logcan. And essentially this logging module works by having that you have this log, that you configure all of the fields, and every field has an for every field that you configure, you have to give it a can ID, and you have to give it which field it is, and then you have a key, name, unit, precision, and whether it's relative and whether it's a timestamp this field. And if you want to log, say, 20 or 30 different things, then you would have to have 20 or 30 of these statements and keep track of all of that. And then when you configure the field, you have to feed them with data. Actually, let me show that. Maybe it's easier to see what I'm talking about if you do that. So let's open, let's do it in the demo file here. We'll just do this, and now we can do auto-indentation as well. And instead of using the things that I have here, I have to fill those in. And this one we could define. And if you go back to the camera, this one is plugged into the VESC now, so we have this logging module here that is plugged in over the canvas here behind the USB. Yeah, the camera is upside down from my side, so it's strange to move it. Yeah, anyway, so suppose we configure one field, and this one will be 0, and we call this one test, or we call the key test, and name test data, and unit watts, precision 3 decimals, for example, and these can be false. Come on, and false. Okay, so that code should run. We can try that now. So I will go to console and do Control W, and that works. So we have configured one field now, and then we can write a loop. While, and we have a program as well. Let's do it like this. And for the log, we have the configuration, and then we have a command to start a log. Let me copy that one too. Let's suppose we do it at 20 Hertz. And this time we will write just one field to the log, and the can ID is defined up there, so we can use that here. And now we configure one field and start the log, and then we want to populate the log, and then there is this command called send log f32. and this is a function that takes a variable number of arguments. In fact, it can take up to 100 arguments because you can send a lot of log fields at the same time. So in this case we will only send one, and we can say that we send let's make an index here, and then we can send a sign value of this one, and then we do add a bit to it and then sleep. And now we will run this loop at 100 Hertz. Actually, let's run it at 20 Hertz. So let's stream this code, and you see that it's running. So we configured one field, we start a log, and then we update this field, and then we can do log stop with ID2. And now if we go to the VESC Express and go to the log analysis, browse the files, open the last one, we hopefully have the thing that was written there. I think this might be something else. Yeah, this is something else. So something in this code didn't work now. Let's see. Yeah, I have to pause for a bit and see what is wrong. Okay, so it was working all the time. The issue was that, this is a side note for this demo, but the issue was that you see that we have one folder, one directory that's called date and one is called no date. And I was assuming it will end up in no date because I don't have a GPS, but apparently my GPS receiver got the position here in my basement, and that means we have a clock on it, and that's why the log ended up in the date directory here. And when I open it, this is the one I made before. No, this is the one I think. Then we can see that we have the test data here, which is kind of a sine wave, and we have the test data text, and we have the unit watts here, which is just something we made up, but that demonstrates how the log works. And now if you would want to have another field, then we have to copy and paste this block, fill in all of this data, and then we have to update this one to send another thing here at the end. Now, suppose we want to have 20 fields or so in the log, then it won't be so clean if you have 20 of these blocks in your code, and also a long thing here, and you have to keep track that, well, this data here belongs to this block, and this data here belongs to this block, and so on. And one way to do that can look quite nice is the same way as the log viewer does that comes in the examples of VESC tool. So in this case, I made a list here, and this list is supposed to represent all of the log entries, and I mean, this is just any list that I can make, and I just have to keep in my mind what I wanted the list to represent. And in this case I wanted to have a key, unit, a name, index, and those the other properties down here is time and is relative, and value. And I want to be able to leave values out and leave entries out of the list, and if I leave them out, I want them to become some default values, because then I can just, if I want to add something else to the log, I can just do test, call it test2.3 for example, and then I can write an expression here where we can do, let's say we want to do in take the input voltage and multiply it by 2. This is actually how I would write that. And now let's try to run this code, see if that works. Stream. I'm connected to the wrong thing here, so I have to go back to the VESC. Stream. I will change the input voltage up and down a bit. And then I will stop the logging here. And now if we go back to the VESC Express, we should have, we can do refresh, and we got a new file here now. And if we download this one, we have a bunch of data, and we also have my thing that's called test3, which should be twice the input voltage. And if we plot them at the same time, we see that this is 25 something, this is 50 something. So that seemed to work. And notice now that what I have in this list here is that I just added this thing, and I just added an expression, and this expression is not evaluated here. This is just code that we interpret as data now. It's just a list, and later on when we do the logging, we look for this code and then we execute that code at that point. So that's why we can just like write the expressions as they say, and it's a very convenient way to make this list. So how did I actually do that? There's probably a million ways to achieve this, but the first thing I do in the code is that I do a range loop. There's also a loop for each, where you can loop over each row, and we can even test that here. So we can do, for example, loop for each log list, call it E entry from the log list, and for each entry we just print it. And we can see that we can loop over the whole list. But in this case I also need an index, because I want, this is entry 0 and this is 1 and so on. So this is why I did a range loop from 0 to the length of this log list. And then in this one here I made a local environment, and this is just that if you don't want to make lots of global variables, then you can make a global and a local environment where you can make some variables and functions that will disappear then when you leave this local environment, to not clutter up the global environment. So here I took out the field first, where I take the log list and I take the index of row, and I call the index you see here to loop over it row. So here's my field, or here's the line in the log list. And here I made a different function, so this can be, it can be data or code, anything. And here it is a function. So I made a function here that's called getField, where I take in type and a default value of the field. So what I want to do is I want to take a field. If I find it here, I can use that value. If I don't find it, I want to use some kind of default value. And then I use this type of, then I make it here, then I do let, and I make another local environment within this local environment within this function. And then I take the first element of field, which will be the first thing in here. And then I check if the first thing is equal to the type that I'm looking for. Then I will first remove the first thing from field, so I will use set var, so update it, and use rest. And there is this first, means I take the first thing of the list, rest means I take the rest of the list. So for example, if I have a list here, we'll just make a list, let's see, def L 1 2 3 4, and then you can see that L is 1 2 3 4. If I take first L, then I get 1, and if I take rest, then I get 2 3 4. So if we found if the type of the first thing is what we're looking for, then we set the field to the rest, remove the first thing, and then we return the first thing in this function. And if it didn't have the type, it returns the default thing. And then we can just make them, so we do key, and then we get field type array. And if you want to know what the type is, you can use type of, and you cannot even do that in the REPL. So if you do type of a string, you get type array, type of a number, you get type I, floating point number, you get type float, and so on. The type of a list, which the last thing is, will probably be type cons, not type list. Makes sense. So this way we say that, well, key is get field. I want this to be a string, and if it is a string I use it, otherwise I will make up a string that is default value. And in this case I make the default value to, I just call it field and the row index here. Even if I leave out this thing, I could also assume that this one will always be there, but I assume that the list can also contain only an expression. And then we do the same thing for unit and so on. And every time we find a value, we'll pop it off the list and look for the next one. And this way we can get defaults for all of them based on the type, and we can initialize the log for all of them. So this thing will run with the default and the values that we set here for all of the entries. So that is really convenient. Here we did just 1, 2, 3, 4, 5, 6 of those blocks, and they only have this much code, and another of those blocks will just be another line in this list where you only have to enter the things that you are actually going to change from the default values. So that is just super convenient. Now the last part, how do we deal with this last part? So yeah, we do the log start, and the number of fields will be the length of the log list, so we already have that information here. And there's that rate hertz and where the log GNS is at the top here, just to have it in one place. And let's see, we can skip this. This is just some event handler that if we shut it down, if the voltage drops, then we'll stop the log to not lose data. But then we have the function here that actually sends the data, and you see we don't need a lot of code for it. So how does this one work? So we use this log send f32. We do the can index of the ESP32, and we say that now we want to send data from index 0. And what I'm doing here is I'm creating a list, and this is, I mean, there's much easier ways to do this, or much different ways. This is an easy way, but it might be unintuitive if you're not used to things like map. But essentially there is a map function where you can give it, the first argument to this function is a function, and the second argument is a list. And this function will then apply this function to every argument and to every entry in this list, and make a new list with the result of this function. So first we can see, look at the list we generate. We generate a range from 0 to the length of the log list, which will be, it will look like this, just a list 0, 1, 2, 3, 4, 5. And then for every index here in this list, we will apply this function. Actually, I can do the whole thing here, just to see what we get. And now we can see that we get those values that we're interested in logging. And the way this works is that we take the index from this function, 0 for example, which we feed in as x here, and then we take the index of the log list for the row of the log list, and in that row we take the last element. So remember, -1 means the last one, and this thing will be the list that we have here, get vin index of this thing, and we want to execute this code, so we just run eval on that, evaluate that thing, and that is how we take those indexes, take out the last thing, evaluate that, and put that in this list. So this is how we generate the list with all of those values, and then we send that to the logger. So that is a super convenient way to do all of this, and the whole thing is like 100 lines of code, including all of my comments and everything. So I don't think I could have done it this easily and conveniently in any other language that I'm very fluent in. Could probably done something in C++, but I think that would have been quite a bit more complicated than this. So yeah, this is a quite convenient way to write code, and it's really nice that you can have it on an embedded system like that.